Hello students, in this video we'll show that sine of z as a conformal map is a degenerate version of our Schwarz-Christoffel mapping. Let's consider the following this triangle with vertices at negative pi over 2, pi over 2, and then pi over 2 plus IR. Okay, so I have a triangle with those vertices over here. So let's draw that region over here. So here's negative pi over 2. Here's pi over 2. And then here's pi over 2 plus IR, where R is some huge number, right? Okay, so this, of course, this triangle is in the upper half space. So this triangle lies in the upper half space. Okay. And so let's figure out what the exterior angles are going to be, right? So I'm thinking about this as a part of the upper half space, right? In other words, there's the real line over here, okay? Now we have three exterior angles over here. We have this exterior angle, I'm calling it alpha. We have this exterior angle over here, that's beta. That's clearly what that exterior angle is. It's just pi over 2, right? And then we have this exterior angle over here, which is what? Which is going to be, I'll call it gamma, right? So those are my exterior angles for this triangle, right? And so I want to figure out what happens to these exterior angles as r goes to infinity, right? So as r goes to infinity, these exterior angles are getting bigger and bigger, right? So in other words, what can we say? We can say we're going to map, let's call these vertices over here, let's call this W1 for a vertex, W2, and then W3. Okay. I'm going to map x1, which is going to be -1 to W1. I'm going to map x2, which is going to be +1 to W2. And then we map x3, which is going to be infinity, we'll map to W3. So I'm going to use infinity as one of my points over here, right? And so now what are my exterior angles over here? As r goes to infinity, we have that alpha is going to what? Is going to pi over 2, right? Okay. As r goes to infinity. Beta is clearly still just pi over 2, right? So what does that tell me? That tells me that my K1 over here is going to be 1/2. My K2 is going to be 1/2, right? So my K1 and K2 are going to be 1/2, right? So K1 and K2 in Schwarz-Christoffel equals K2 equals 1/2. And for them to sum to 3, we need K3 to be equal to 1, right? So K3 needs to be equal to 1, right? In order for them to be a closed polygon. And so if that's the case, right, that's my third point over there, then what's going to happen over there? That says that K1 times pi is equal to pi, right? So K1 times pi, or K3 times pi is equal to pi, right? Excellent. So in other words, in the limit, this is true, right? And this is valid as r goes to infinity. That's a valid transformation, okay? Good. And so what's going to happen to this region? This region is going to transform into what? This region is going to transform into this thing over here, negative pi over 2, pi over 2. And we know a conformal map that takes the upper half space to this. We've already seen that, right? That's sine, right? So we note we already have that sine of z is a conformal map from the upper half space to the strip. What's the strip? It's the set of z such that negative pi over 2 less than the real part of z less than pi over 2 and the imaginary part of z is greater than 0, right? That's the strip it maps to, right? This is exactly just that strip over here. And then this is S over here. Great. And so now what? Let's do the calculation. Good. So now what's my Schwarz-Christoffel mapping? The Schwarz-Christoffel mapping is going to be what? Is going to be f prime of z is equal to a, and I'm going to have a z plus what? Z plus 1 to the negative 1/2, and then z minus 1 to the negative 1/2, and then infinity is chosen in such a way that you get to that point over here, this point over here is W3, right? Excellent. And so now, oh, we're in a good shape because this is really just a, or a prime, z, let's write like this. Let's write like this over here. I can write this, of course. This, by definition, is just going to be a z squared minus 1 to the negative 1/2 power. I can pull out an I and change the constant over here. So it's a prime, and then 1 minus z squared to the 1/2. Great, so that says that f of z is just going to be a prime sine inverse of z, right? Plus b. Okay? Yeah, and so vice versa, right? I have this vice versa. So this is, we know that this is a conformal map from the strip, right? So I have to change this up a little bit. So it's a conformal map from the strip to upper half space. From the strip, S defined by this formula to the upper half space. Plain. Okay, good. All right, excellent. And so now what? And so now, what can I say? When I plug in negative 1, I have to have what? I have to get that negative pi over 2 is equal to what? Negative pi over 2 has to be a prime. Sine inverse of negative 1 is negative pi over 2 plus b. And when I plug in 1, I have to get pi over 2. Pi over 2 is equal to a prime times pi over 2 plus b, right? Good. So what does that force b? If I add these equations together, b is equal to 0, and a prime has to be 1. So this forces a prime to be 1. A prime is 1, therefore your conformal mapping w is what? W is sine inverse of z, right? Now this is a mapping from what? Sine inverse of z is a conformal mapping from the upper half space onto this strip, right? Therefore, sine of z is a what? Is a map from the strip to the upper half space. So we proved that in this case, this is a conformal mapping of the upper half space onto the strip, and that gives me that sine inverse is actually conformal mapping the backwards direction. So it makes perfect sense, right? Because we already knew the result that sine, what? We know that w equals sine of z is a conformal that maps the strip to the upper half space. Therefore, we now know that sine inverse is a map of the upper half space to the strip. So we got one of these degenerate versions of Schwarz-Christoffel, which gave us an intuition for a conformal mapping that we'd already studied. Very neat. Thank you very much.